All right. I'll assume this is working. Just by a little background, I was thinking about basically the entire sweep of my career. And what was it that really made computing really important? And I remembered at the end of my first year at the Air Force Academy, which had the only computer science department in the world, because nobody else had figured out. The professors were all arguing that this couldn't be for turf. And so they say computer science is not a real by itself. But the Air Force was the most advanced user of computers. And so they decided that they were going to do this. So in the summer after my first years in computer science, I was walking on July 9th, 1969, in an airport, and I watched the moon landing. And it was a remarkable time to be a theoretical computer scientist, because it was a time when innovation was happening, but the computational capabilities were very, very small. In fact, the entire moonshot could be done on one chip, and you still have lots of power left over. But for me, it was a symbol, because when I started looking at computer science, it wasn't that it was cool to program or anything like that. What I realized is there was this thing called algorithms. And these algorithms, as about my third week in the first course, I looked and I said, these algorithms, they're theoretical. You can do anything, and everything in the world is going to change, because these algorithms will change data in everything. And so that became my passion, not only to be a good computer scientist, but more to understand why we were doing this and what its impact was. And so that's what this talk is about. I'm talking about supercomputing and its relationship to possibly what's been going on. If I get this right. Yeah. So high performance computing came about not because computer manufacturers were any good at it. Every company was doing various things, but there was one individual who actually started because he wanted a job, and he had just graduated from the University of Minnesota in engineering. A mentor of his said, go to the airport in Minneapolis and knock on this door of this hangar and tell them that you want a job. And that was the first commercial company that did computers. And from that day forward, Seymour Cray was totally focused on what we can do with these things and make them faster. He wrapped the first memory. He changed the ways of doing things. And his passion was to do things right in a way that would make it faster and faster and better and more reliable, because he realized that that was the way to change the world. Yeah. He was a very humble man. Most people never heard of him, because he just was a guy in Wisconsin who was passionate. So that's where I lived with him. I remember the first time I met him, I was a new officer at the Cray Research Company, and I was actually going to be asked to be speaking on behalf of Seymour. So I spent an hour with him. Like everyone else who met him, had changed my life. So what was this about? The question that he wasn't trying to make money on a computer like IBM. He was trying to say, what are the hard problems? What are the new possibilities? Very similar to where we are with quantum. he had unbounded focus. I've never met someone who was so focused. And he was focused on delivering, on innovating and not getting the credit. We had in that company, Leadership with Passion. There was a book called In Search of Excellence. Cray Research was cited, was a case in MIT as the best run company in the entire technology world. Because everything we did was collaborative. Everything we did was for a purpose. And that's what made it great. So all we did is we had innovation looking beyond what anyone else could do. And every day in the laboratories, that's what they were doing. They were creating new circuits and things like that. The other thing that was important, amazing in this company is right up to the top, from top to bottom, it was a company that had excellence and ethics and passion and always told the truth. I hope that you get to work for companies like that. There are very few. But the end product is that what he did changed the world. And it changed the world because of the kind of person he is. And what happened that I'm going to talk about a little bit, I've been asked to talk about, is what really made it possible. And it was possible because it was the consensus of political, commerce, academic, and value creation. So in essence, the entire impact of Cray research and supercomputing came about by a mix of political and policy work as much as the scientific work. Now, before I go any further than that, you hear about politics. You say, oh, I was hired as an executive to be the policy person. I understood computing. I love theory, but I was one of the few that in my gut, I just had lived politically. We had no PAC. We did no lobbying. We did nothing like that. We simply did the right thing and then made it possible. So what happened as we started, the Cray one computer came out in 1977. Suddenly, this was by far the fastest computer in the world. In history, it could do all sorts of new problems. We could start to do algorithms that could not be done on any other computer. And it was clear that this was going to be the launching point for all scientific progress. And so what I did is my job was to sense what was going on and why it was important and in the political side. So in 1983, there was a launch of the High Performance Computing Initiative. It's a national initiative. It is still going on, but what it did was brought all the universities together, all the players together, and made it into a national priority. It was amazing to have the job that I had, because they realized in every sector that this was critical for everything that we had. This was a time when things were very tense around the world. The Cold War, lots of other things were happening. Part of the Cold War was ending later. But and I'm going to end the topic with one really important story that you like. So what happened was policy became the game changer for computing. Not policy because we convinced politicians to fund this. We never accepted anything. But policy is the way we think about these things. What is the importance to society? How can we get better? And Seymour Craig never missed a beat. Everything he did, he was always doing the next thing. Toward the end of his career, a few years before he died, we had all sorts of fascinating things. And one of them was, well, let me give you an example of the DOE, Department of Energy, and the Defense Department was responsible for all of the missiles. And one of the problems they had, they said, how can we have a missile that's going up and now comes back into the atmosphere and starts getting so hot? How can we look at the deformation and control that? It's a very hard problem. So they created this code that did the first three-dimensional analysis of deformation. And one day, about a year later, that code, which was deep in Livermore laboratories, someone said, you know, that can be used for three-dimensional building of anything. Would it be all right if we made a code and put it out in the open? And that became the code that changed the whole way in 1 year that around the world that they designed cars. The next year, almost all the cars started looking the same. There were all kinds of crazy fancy things before that, and they always look the same. And the reason why? Because they all discovered that the fluid dynamics and physics doesn't care what car model you are. If you want to go smoothly, everyone has to follow the laws. But for the first time, we could compute them. And in every field, this happened, went across every field. And so then this program is still keeping going. And it's a national treasure. But now we see that it's something that can contribute to research in places like quantum and everything else. So let me run you through a little presentation, and I'm going to go fast because it has a lot of slides. But this will give you a sense of what I had the privilege of talking about for most of my career. I was asked to give a major presentation and on the future. And this is, so the key is we live in a world of chaos and complexity. But chaos and complexity turns into dollars and decisions. So the question is not how can we play on computers, but how can they really be helping with the bottom at the end? And so we created an economy of optimization that went into almost every field, from medicine to cars to everything else. Thomas Watson, the owner and founder of IBM, just after World War II, they hired a consulting firm to figure out is there a market for computers. And they decided the end of this big study was that there maybe would be a market for 5 computers a year. So IBM was just a little late in entering, right? Because they thought that there's no use of computers. But this is something I wrote in the first time in congressional period relating to supercomputing. I asked my colleague, who was the chief executive vice president, to come down and read it, but this was the end of my testimony. The world is on the verge of a major computing revolution as supercomputing is applied across a broad industrial science base. The only question at this juncture is which nation will choose to lead that revolution. And that is the question that we need to ask today. The question, there's all sorts of research, all sorts of things, but we're looking at these things like quantum, and we're saying we have to do it. We don't know how to do it necessarily, but we have to do it because it's important. Now, the key to Cray was a few pieces of hardware. He figured out how to accelerate almost everything in the computer. And so we went to scalable high performance computing and it started changing everything. When you looked on a global scale, you're going to be in leadership. All these pieces of policy interact. Because what you're trying to do is you're trying to solve problems, but to solve the problem, you have to step back and have the pieces. And then you have to step back and say, where is it going to work together? And so this was what also happened is we became the top expert in the testing and evaluation of these circuits. The discipline that took and the amount of work that it took to understand that was a lot of what we did. What we discovered also in the entire economy, the more you put supercomputing, which is now, by the way, the first Cray computer, your phones is 1 million times more powerful and several million times the amount of memory. That first one was $8 million. 4 million was for the memory alone, and the memory was 1,000 words. So we've got something to scale. But what we were looking at is we suddenly realized this is changing everything. And so it made us look back and change the way we build things. So we also looked at the different kinds of markets. There were the markets that were big money markets, oil business, everything by then. But then there were the questions that people didn't have access, but needed to solve. The high performance computing program allowed us to be able to share across that and change a lot of other computing architectures. So basically what we do, this is how innovation, this is a number of years ago, back in 1983, when we were preparing for the first legislative conference, I was asked to have breakfast with the chief of staff of the science committee. And in the middle of the conversation, I was trying to explain something. I said, well, let me show you something on a napkin. And on that napkin, I drew some papers and realized, you know what, really, everything's converging. All the technology is converging. We've all seen trust, and we're seeing a whole new movement in everything. And I realized that it wasn't only supercomputing that was changing the world, but the pieces around it. Communications for the first time. The web happened because of supercomputing. It did not happen because of darkness. The internet actually happened because of supercomputing. DARPA had a military network. Part of the new program, the master program, was the idea that we would have 4 major centers that were owned by the National Science Foundation, and no money would be spoken of, it would allocations of researchers at any university in the country would be on time. So when I was asked to architect that, I said, well, the one thing we need is we need to have communications, some access, so that everyone in any major university could have some direct online access. And at that time, there were several hundred IP networks and all proprietary. And so became an idea, what if the NSF created a connectivity from all these, so that all the universities could have access, if they were granted it, to one of the 4 supercomputer centers. That was launched in 1985, and 18 months later, 16,500 subnetworks around the world plugged in. And that's what we call it here. And they plugged in because for the first time they could share research data. And one of the people that was particularly excited about this was someone in Switzerland who always wanted to be able to share the data that Stanford had with this accelerator. But it was too much data. When this network plugged in happened, he sat down for 3 weeks and created the web. Then some graduate students at the University of Illinois, which had one of the 4 centers, their sponsor for research said they didn't have any research to do for the summer, but they could do whatever they wanted. And he said, well, can we do a project? At the end of the summer, the browser was created by a couple of graduate students. Later, I was asked to chair a group of people that came from the various government and outside organizations on the idea of having a national communications infrastructure. And that became the official internet. But it was all because the idea of sharing and being able to do this was for everybody. So these are charts, every one of them is a whole idea, but you can see this was just the way that I was thinking as I looked at and started realizing all of these things that had happened, what it was changing and why it was changing, and what this convergence was going to do for the next generation. And as you can see, it was doing it in every area, going back to the 40s to 2000. And you can see what was happening is as these things were coming together, that's when PCs started happening and all that stuff too. So what happened is, in my view, is 5 technologies have come of age. And these together, we're going to change the entire way our society operated. And it all, at the end of the day, the beginning was because one man never gave up. And so it went around the world. We also had problems with policy because we didn't want any Soviet Chinese folks, anyone who was against us, to have access, because the computers, most people had, even users had no idea how powerful these computers were. But the NSA did figure it out. And there was a policy that we couldn't even sell to anyone who would allow one of those folks, because then they would know how powerful the machine is with new algorithms. And those algorithms became algorithms that later were some of the algorithms that they thought would be really good for quantum. Remember that conversation years ago. So what happens is you start to then have an interesting thing. Instead of one curve of R&D, everything was an R&D. So you had all these new, completely new ideas. How we have data, everything, every piece of data. It was all operating systems started becoming 5 or 6 or 10 separate. So it was interesting because this was, I created this chart when I was at another supercomputer company after I had left Craig to do some public service, and then was hired in another company that was highly parallel. It was the first company that focuses totally on data. And so that was when I created this chart. So at the end of the day, if you want knowledge to be optimized, you need to put it in context. And these are the things that we're trying to do in high performance computing and in the next generation of these algorithms. What we're trying to figure out is what's going on and what's going to be the discriminators. And we have to be very good at it. I've given many talks on each of these things, but you see, the idea was people say, well, that's just scientific computing. Well, then business discovered that they need that kind of computing for everything. Amazon has AWS because they have extra bandwidth, because they had to put all those things in place to run what their operation is. And that goes to, so what we're doing, the main thing I'd like to point out is we are in a time of fundamental change, innovation across every area. And the question is, how are we going to integrate? How are we going to make it work for us? And how are we going to do it responsibly? So I could take you through, but at the end of the day, people solve problems. Computers don't. And I want to end with a very significant story about the way something happened that changed everyone's life. In the mid-'80s, in 1983, to be specific, we had a salesman who thought, gee whiz, shouldn't the medical research community have a use for this computer? And what he did is he started reading it, and particularly he started reading things about the genome and about those, and he wasn't a scientific guy, but he just poured himself. And so then he went to see the National Cancer Institute. He started talking to some of their scientists and saying, you know, maybe you can use this kind of computing. And Dr. DeVita, the head of the National Cancer Institute, got excited. My job was to work with the secretary of HHS to make sure they said it was all right. And the thing that was true at the National Institute of Cancer is they were the only agency that could spend their money in any way they wanted without any permission, because the National Cancer Act said cancer, they control whatever they're going to do, because this is a national problem. And so Dr. DeVita announced that he was going to create a whole setup, $50 million expenditure, new building, a new center for computational biology that didn't exist. And in one of the final days before it was approved, he was called to the House of Representatives. And after the various testimonies, the chairman looked down and said, Dr. DeVita, I know, and you know you have the money to spend because you don't need our approval. But $50 million is a lot of money. And this was in 1983. And the average grant, major grant for researchers was only $50,000. And the whole community was up in arms about this. He said, can you promise us that you will make a breakthrough? Dr. DeVita gave one of the most remarkable responses I have ever heard in all my years watching politics. No, Mr. Chairman, I cannot promise you anything, except that we can't afford not to try. That word was so powerful. I still remember. And not long after that, the chief of staff of the minority staff of the science committee and I decided there must be a way we can help them know what to do, because nobody had ever used gear like that for any research, except the defense intelligence, defense agency that was using a Cray computer and had unwrapped the ability to model the human cells and everything to see their impact of radiation. So they had all the crystallography codes in their back pocket. Nobody else had them. I called a friend of mine who had run all the computing at Los Alamos for years, and he was retired and speaking around the world about supercomputing. And I said, would you do me a favor if we pay for your trip? Would you come and spend a weekend with people at the National Institutes of Cancer Research? And he said, Brett, nobody is doing that work. Why are they buying your credit? And I said, well, just trust me. Come. And I still remember Sunday evening. He called me while waiting for his plane home to New Mexico. And he said, thank you, I will never forget. David, it's computational biology was born today. And that changed medicine, health, and everything. Because someone said, I'm not afraid to try. Thank you. Any questions? You only have to have one slide. You don't have to hear the whole thing if you have a question. Okay. Yes.
We see substantial budget allocated in the field, and we see the legal support for the research. I'm just wondering, is there a direct impact to the town? In their R&D, or do you have to decide who we deal with the big house and market them?
That's a good question, because there's a hard differential between the money that's being allocated in general and research grants.
Okay.
That's what you're asking.
Right.
Yeah. Well, what is happening is that, and it's the first time this has happened back in the starts. It's the first time that these kind of grants would automatically be considered important. So they would listen, and a whole division of NSF was created for that. So what it did, it dramatically accelerated the amount of particularly faculty researchers and that's really where most of the innovation came from. It was much easier, but like everything else, unless it's really written in the program, it's tough. So
there is I think. So, for example, the one building this industry take they jump in first, and that we have the initiative.
Convincing people who are political, not Republican Democrat, people that are in policy and budgets and things like that, convincing them that something is important enough to have a major thing like this. Yes, it's very hard. Very hard. And one of the advices that I get people at universities, particularly when I've asked a lot, and I knew a lot of countries, that the clear is you have compassion, you have to be detailed. You have to have a reason why. Because none of those grants were given when that major issue happened. People just said, I want them to. And it really changed the way they were going into the issue. Because they had to be engaged. And the other impact was since the 4 centers were at major universities, but they were not owned by the university. They were just the babysitters of these things. Those things were created with a necessity of collaboration that most university centers would never have put up. I helped actually establish the policies at some of the centers. And one of the most important examples of that is the San Diego